Now what I want to do is do a summary of all of the integration methods that we have learned. What we learned last semester, as well as what we've learned just over the past week. So this is called Summary of Integration Methods, and it's to prepare you for your quiz. All right? So, the first method that we learned back before Christmas break was u-substitution. And that is an integral of some function of u and a du to go with it. Okay? Usually, if there is only one x, it's going to be possibly a u-substitution. Every once in a while, it's an integration by parts. As if you have an only one x and the derivative is 1 or a number, you're fine. But the thing that makes u-substitution unique is that you have a function and you also have its derivative or something you can make into its derivative by multiplying in a constant. Okay? So, please write this down. If there are two x's in the integral and one is the derivative of the other, then use u-substitution. Okay, if you have two x's in an integral, either multiplied or divided, and one is the derivative of the other, you will use u-sub. Now the way it works with fractions, the top has to be the derivative of the bottom. If they're multiplied, it doesn't matter which one's u and which one's du. Okay? So let's look at a couple of examples. Let's look at this one. The integral of sine of x cosine of x dx. Trig functions are a little tricky, but what you have to know are your trig derivatives in order to correctly deduce what method to use. Now, is one of those x's the derivative of the other one?
Yes.
Yes, and actually it could go either way, couldn't it?
Yes.
It could. So in this case, u would be sine and du would be cosine. So this is a u-substitution problem. I'm not going to work it all the way out. I'm just letting you see that if one is the derivative of the other, then it's going to be just plain u-sub. Okay, let me give you another one. What if you have the integral of x over x squared minus 4 dx? X over x squared minus 4 dx. Okay. This couples with a method I'm going to talk a little bit more about later called partial fractions. Okay. Now, partial fractions is recognizable by the fact that you can factor the bottom. Can you factor the bottom of that right there? Yes. Okay. But let's not go down that road unless we have to. Okay. Is the top the derivative of the bottom, or could I make it the derivative of the bottom? I could make it. What do I need to give it? A 2. It just needs a 2. So in this case, u would be the denominator, du would be 2x dx, which means I would need a 2 out on top with the x and a 1/2 outside. If you can fix the integral to where the top is the derivative of the bottom without factoring and splitting your fractions and all that stuff, this is much faster. Now, I believe that this problem could be done with partial fractions, but it's a lot more work. Okay, this is a very simple u-sub. Very simple u-sub. Okay? So be careful. This is not partial fractions. Okay? Now, like I said, I haven't tried it, but I think it could be. But partial fractions is more work. U sub is the easiest method of all. Actually, easier than that is just take the integral of each term. That's the easiest method of all. Okay, so the key for U sub, one is the derivative of the other. Okay? Do you have any questions for me to this point?
No.
Nope, I didn't figure. Number 2 is integration by parts. I'm going to underline these so they stick out a little bit more. And this one is the integral of some function of u, but the derivative of something else. F of u dv. I don't like putting just a plain u right here because you got to realize it's not going to just be an x. It could be sine of x. It could be, you know, e to the x. You don't know what it's going to be. But some sort of function, but somebody else's derivative. Okay? So they have nothing in common with each other. All right? This is the situation where we have two x's, or two functions. Let's change this to functions. Two functions multiplied where one is not the derivative of the other. This is the situation where you have two functions that are multiplied where one is not the derivative of the other. At the very top of the screen you can see sine of x cosine of x dx. If it had said something like sine of x secant squared of x dx, the derivative of sine is not secant squared and the derivative of secant squared is not sine. So that would be a situation of integration by parts. Okay? So, how do we do this? There's a formula that you need to have memorized for the quiz. And the formula is the integral of u, some function u dv. Who remembers the acronym to remember it? Ultraviolet voodoo. So what do we write first?
U times v.
U times v.
Integral.
Careful, what sign comes next? Minus the integral. What is voodoo?
du.
V du. Voodoo. Ultraviolet voodoo. Okay? That's the formula you need to have memorized for this process. Okay? Now, there were two special cases of integration by parts I want to talk about. We're going to call this one part A. Now that's just a generic one. You do it once and you're done pretty much. Okay. Version A is when you have two what I call looping functions. Two looping functions. Okay. There are three functions that when you take their derivative or antiderivative eventually come back to where they started. E to the x is one of them. Now I'm going to put e to the kx. It could be any number up there. E to the kx. What's another one? Sine of kx. It can be any number in front of the x there. And cosine is the other one. Those are the three looping functions. They eventually come back to themselves when you take their derivative or antiderivative over and over again. If you have two out of the three in one integral, you have to do a special case. We did one in the notes where you have to write down the original problem and you end up with the same integral on the other side and you move it over and add them together. Does that sound familiar? You'll have to look at your notes to remember that. You will have to combine two integrals. And I'm just going to say look at notes. I'm not going to work it all out because you can look at your notes to see that. And for those of you watching the video, if you go watch the integration by parts video, I do a sample of this problem. Okay? So, version A is two looping functions. Version B is one looping function. plus one polynomial function, which is x to the power of n, where you have x to the, 5x squared, 3x, 2x to the fifth, something like that. More of a power function scenario. Okay, so one loops, and one is an x that when you take its derivative, it will eventually go to 0. What method did we use to do these? Do y'all remember? The which one? Not tubular. Tabular. This is okay. What's the root word of tabular?
Table.
Table. It's a table of values.
I was about to say taboo.
Taboo. The tabular method. And remember that the columns are sine, u, and dv. The signs go plus, minus, plus, minus. The x to the n goes under the u. And the dv is the looper. Whatever loops goes under the dv. Let me move that up so everybody can see. The signs go plus, minus, plus, minus. The u is always the one with the x, so that when you can take its derivative over and over, it eventually gets to 0. And then the dv is the looping one. And remember that it diagonally, it does a weird connection this way and then down. This way and then down. Okay? So you need to know how to do that for the quiz as well. I can guarantee pretty much that there will be one of each of those on there. Okay? Questions? Are we good so far? All right. Now, give me just a second to make some adjustments here and go to the other piece of paper. Method number 3 was partial fractions. Partial fractions. And this is where you have a scenario of the integral of dv over u. Now, I never really talked about it that way in the video, but it really is a dv over u. In other words, you have a denominator where the top is not its derivative, and it can't be made that. Also, I want to add that u is a polynomial. Very rarely, usually a polynomial. I don't want to say it 100% ironclad. It is usually a polynomial, something that you can factor. And the top is not its derivative. Top is something else, something missing x's, usually. Okay, so I'm going to write in parentheses, the top is not the derivative of the bottom. That's when you use partial fractions. Okay, so what I want to do with this one is to write out the steps. What do we do? Because it's not just a standard plug it in the formula and just do it. There's more to it than that. I'm going to do it with an example. So we're going to have the integral of 3 over x squared plus 7x plus 10 dx. Now, because I just pulled that function out of the air, I don't know if it comes out nice, so I'm not going to work it all the way. We're just going to list in words what we do. We're going to do a little bit of it. Okay, what is the first step we do when we see something? Well, first of all, do you see that the top is not the derivative of the bottom? What is the derivative of the bottom? 2x plus 7, and I don't have an x anywhere. So I have to use partial fractions. Okay, what's the first thing I do? Factor the denominator. And like I said, I promise you that the denominator, number 1, will always factor, and number 2, it will always factor into linear factors, no x squareds. So if you end up with an x squared down there, you can factor it more. Always. Okay? There are problems where it won't be linear factors, but that's beyond the scope of this class. Okay? After we factor the denominator, we write the problem as two fractions. So this would become, for example, something over x plus 5 plus something over x plus 2. Those are the two factors in this case. Who remembers what we did next?
You cover up one of them.
You cover up one of them.
And find the number makes the denominator equal 0.
Okay, so before you cover it up, you asked me what makes this 0, which is what in this case? -5, and then you go plug -5. Actually, you cover up the factor over here, and you plug in -5, right? So, the next step is find what makes the first denominator equal 0. I'm abbreviating. Find what makes the first denominator equal 0, and then plug in to the original problem. And I'm going to put in parentheses, cover up, because you'll know what that means, to find its numerator. To find its numerator. And your numerator will always be a constant. Okay? So then you end up with a number on top of this fraction, you end up with a number on top of that fraction, and then you just integrate the individual fractions because now the numerator is the derivative of the denominator. So, how did all our answers look? What kind of function did they turn into? LNs. And that's a big one. All will be ln functions at the end. All will be ln functions at the end. Questions on that? Okay. Number 4, the last one, is improper integrals. This is what we did yesterday. We finished yesterday. And we coined a new name for these yesterday. Do y'all remember what we called them?
Integral.
Integral, that's right. One of the versions is an infintegral. And that's a situation, I'm going to put a version A. This is when you have the integral from a to infinity of f of x dx, or the integral of negative infinity to b of f of x dx. Okay, these are pretty obvious. If you see an infinity, it's an improper integral. Pretty obvious. All right, so let's talk about what are the steps. What do we do? How do you do these problems? What do we do? Replace infinity with a or b, usually. Then what? Yeah, take the antiderivative, exactly. Take the antiderivative. But finally, what are we putting in front of this integral to take care of that infinity? A limit. We take the limit as the variable approaches infinity. Okay? Now, real quickly, I'm also going to put a little helpful hint out to the side, and this is going to be just a study box with 4 squares in it. And these are the 4 different results you will get when you have an infinity situation. Okay? Now, these are limit values, remember? These aren't necessarily what they equal when you plug it in. If you get a number over infinity and you're taking a limit, what is the final result going to be? It is going to be 0. Because remember, infinity is like a trillion. What if you have 2 over a trillion? That's very, very small, very, very close to 0. But if you have infinity over the number, what is your answer? Your answer is infinity. Okay? See the difference? Now let's go the other way. What if you end up with a number over 0? This may happen sometimes, not necessarily on these problems. You need to know this. That is infinity. A number over a number very, very close to 0 is approaching infinity. But 0 over a number you learned in middle school equals 0. Very good. So make sure you know all of those, especially when you do these problems. I forgot to add one thing last period, and I'm going to do it now. If the limit approaches infinity, does it converge or diverge? Diverges. Equals diverges. If the limit approaches a number L, it could be 0, -2, 5, whatever, that is a converges. Capital L is the common letter used for talking about limits. It is what they usually say a limit is. It's capital L. All right? So the last kind that you might see of these is when you have the integral from a to b of f of x dx, where you don't see an infinity, but f of a or f of b comes out to be a number over 0. It's undefined. So if you plug in one or the other limit, you get undefined. Excuse me, one of the other limits of integration, you get an undefined. Okay. The procedure is to change the problem to the limit as a approaches, boy, this is hard to write in symbols, the number, either positive or negative. I'm going to have to do a sample. The integral from a to b of the function. That's really not good. Let me do it a different way. I'm going to write that down, and it's kind of like, doesn't make a whole lot of sense. It'll make more sense with an example. Okay. The example is going to be the integral from 0 to 1. Which of those two values, if I plug it in, is a problem? 0 or 1? 0 is. So this will become the limit as a, because it's the 0, approaches 0. And I will figure out the sign in the middle, leave a little room. Integral a to 1 of 1 over x dx. So the a replaces that bad value, but then I need to decide, is it from the left or the right? Do you remember how we decided that yesterday? Use your hands to help you. 0 to 1, area's in the middle. Which side of 0 am I on? I'm on the right. So this needs to be a right symbol. All right. So this is what the quiz is about. This is a summary of all the different kinds of integrals we know how to do, and this is pretty much all we're going to learn how to do.